and welcome to today's grade 11 physical science lesson. Today we are carrying on with Newton's laws and we're going to explore Newton's second law further. So as we always do, we start with terminology. So I'm going to put up a few terms for you and we will take it from there. So I want you to have a look. I want you to tell me what the following words or terms mean. Independent variable, directly proportional, and inversely proportional. So I'm going to give you 2 minutes. I want you to just write down what you think these words mean, or what the terms mean. Ask a friend if you need to. 2 minutes starting now. Okay, everybody, so hopefully you've got an answer for me. Let's compare what you've got to what I've got on the board. So let's look. For the first piece of terminology, what does the following word or term mean? Independent variable. So I have here that the independent variable is the variable that the investigator changes. So in other words, you are doing the investigation, you make the change. Okay, so that is the independent variable. Something is going to rely on what you do, what change you make. Okay? Then directly proportional. This is a relationship in which the values of dependent variable change in the same ratio as the values of the independent variable changes. Okay, that's a lot to take in, so let me go through it again. I'm going to go through it slowly and underline the important parts. It is a relationship, that's the first thing, in which the values of the dependent variable change in the same ratio, important word that, as the values of the independent variable. Okay, so because we're talking proportion, proportion means that we need to talk about ratio. Okay, I hope you remember that. Make a note of it if you didn't have that in your definition, please. Then inversely proportional. Again, a relationship in which the values of the dependent variable change in an inverse ratio to the values of the independent variable changes. Okay, so slowly, what does it mean? So it's a relationship, again, involves a dependent variable. This time, the change is an inverse ratio. Okay, so what does that mean? That means as one value increases, the other value is going to decrease by the same proportion. Okay, remember I said to you proportion is important. So as the one increases, the other one is going to decrease in the same ratio or by the same proportion. It's really important that you remember those. So proportion, remember we're talking here about ratio. And then, of course, we talk about the independent variable. Please just make a note. This word, inversely, okay, please use that word. Do not use the word indirectly. Okay, please use the word inversely. And then for the other proportion, it's direct proportion. So now, what does this mean? What does inversely proportional or what does directly proportional mean? What does it mean to us as scientists in the laboratory? Let's have a look. I'll give you an example here. If the independent variable doubles, okay, so doubles, then the dependent variable values will halve. Okay, so remember I said to you, if the one value increases by a certain amount, the other one is going to decrease by the same amount or in proportion or in the same ratio. So this one doubled, the dependent variable halved. Okay, so independent variable, you made the change, you made it double. That means the other variable had to halve. Okay? Dependent variable is directly proportional to reciprocal. Okay, goodness, what does this word mean? Reciprocal means, in maths terms, 1 over. So I'm going to say here 1 over x. So my reciprocal is, in mathematical terms, the 1 over. Puts it into the bottom of the fraction. Okay? We've had a lot of words. Can we represent this in another way besides words? And we can use a graph. So if I have that as my set of axes, what I'm going to have as my graph is going to be that for my inverse proportion. Okay? Remember, as the one value has increased by a certain amount, the other value decreases in the same ratio. But just so that you can make sure, I want to compare it to direct. Again, I'm going to give my axes, and my direct is going to go like that. It's going to be a straight line that goes through the origin, and it's going to, again, change in ratio. Okay, so we can represent it in words, we can represent it in diagrams. Let's see what else I've got for you. Something we need to remember. A straight line, like we have in direct proportion, gives you a constant gradient. Okay, so hopefully your brains are going to maths. Maths is important here. Yes, maths is important. We need to understand our graphs for a lot of Newton's work to make sense for us. So if your maths is not so good, I suggest you tune into the maths lessons and ask your maths teacher for a little bit of help in this section. Okay, but back to the science. A constant gradient for a straight line, and it'll pass through the origin. So that's the 0, 0 point. Okay? If it's plotted for the reciprocal, I'm going to draw that down here. If it's plotted for the reciprocal, I'm going to have my value, and the 1 over, remember, was reciprocal, and that is going to give me my straight line. Okay, so just to make sure it makes sense, let me label this one as y, and that one as x. Okay, so when we're plotting the reciprocal, the 1 over, I get a direct line, y plotted against 1 over x. Okay, so just have a look at the 3 different graphs. I want to put all 3 of them up just to make sure that you've got this right in your head, what an inverse or a hyperbola looks like. So that'll be for my inverse relationship over here. When I have a directly proportional relationship, it's a straight line, but remember the change is in ratio. And then when I have this graph, my inverse and I want to convert it to a straight line graph, what am I going to do? I'm going to use the reciprocal 1 over. Okay? And I will end up with a straight line that goes through the origin, but the difference here is that we've used the reciprocal. Okay, hopefully everybody's tracking with me. Let's carry on. Acceleration. So why am I asking you to just think about acceleration? From last lesson, you'll remember that I told you that Newton's second law is represented by F net equals mass times acceleration. So we need to understand what acceleration is. So thinking back to your kinematics or thinking back to your equations of motion, you should remember that acceleration is equal to your change in velocity over your change in time. Okay? Acceleration is a vector quantity. That means we're going to need direction. And just to help you remember that acceleration is meters per second, I'm going to put the units in. What are the units for velocity? The units for velocity are meters per second, and the units for time are second. And because the seconds are at the bottom of this fraction, we're going to end up with meters per second. I'm getting too excited here and I'm writing the wrong numbers. Meters per second, which gives us meters per second squared. Okay, it should be meters per second. We get a little bit lazy and say meters per second squared. Right, now you know where acceleration comes from. You're going to need it a little bit later in your syllabus when we talk about momentum, but for now, let's apply it to Newton's second law. Just to remind you what Newton's second law says, it says the following. The acceleration of an object, so you see, there's our acceleration, is in the direction of the resultant force. Remember, it's a vector quantity, that's why we need direction. So acceleration of an object is in the direction of the resultant force acting on the object. So the acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. Now you can see why I gave you those terms, why we need to know this terminology. We need to understand directly proportional. We need to understand inversely proportional so that when we have Newton 2 problems or we have questions involving Newton 2, we're able to explain them mathematically using graphs, using numbers, and we can also explain them using words. Okay, so those three things, that's why we need to know what these words mean. Let's just quickly revise what the equation is. For second law, Newton's second law, F net equals mass times acceleration. And because one is directly proportional and the other is inversely proportional, we can represent it on the graph. So we've said F net is directly proportional to A. So force is directly proportional to acceleration. So if I draw this in here, I can draw that graph just to make sure that it's in the right place through the origin. Right. So my F net, so here my force is directly proportional. So force directly proportional. That's what this graph means. To acceleration. Okay? If we move on, what is the relationship between acceleration and mass? Here, our relationship is an inverse or a hyperbola. So acceleration is inversely proportional to mass. So this is our hyperbola, and this is an inverse proportion. Okay, so as one goes up by a certain amount, the other one's going to go down by the same proportion or ratio. Okay? Finally, if I take this graph and I do the reciprocal, so if I take that graph and I now want to use the reciprocal, I'm going to end up with a straight line again. Okay? But the important part here is the reciprocal. Right. What I'm going to do now is I'm going to give you a break. We're going to go to an ad break. You are going to just give yourselves a little bit of a brain break. Just get up, stretch if you need to. We've gone through a lot of terminology, a lot of theory. I'll see you after the break. Welcome back. Hopefully you've been able to just settle your mind. You're not so worried about all these words and graphs and maths and all of that sort of thing. We can put all of these concepts together and then work really nicely and work well through Newton's second law. So what I've done is to just give you a break from the big words and trying to think of all the maths. We're going to talk about an experiment to do with Newton's second law. So some of you might have been able to do this experiment already. Some of you might be coming up to do the experiment, or perhaps you're just going to read through it in the textbook. Whichever one it is, I want to go through it with you. So follow with me as I read through the experiment. So the first part is the investigative question. It asks, what is the relationship between the resultant force on an object and the acceleration of the object if the mass of the object remains constant? Okay, so let's just see what we've got. We've got resultant force, we've got acceleration, and we've got mass. So we've got the three things from Newton's second law. So those three concepts are there. What are we going to use? First thing we're going to use is a ticker timer and a tape. We're going to use a ticker timer trolley, a trolley track, so somewhere for the trolley to run, string, and mass pieces, something to give this object extra mass. And this is what it's going to look like. Okay, so our mass piece is down the bottom here. The trolley is going to run that way. We've got our ticker timer that's going to be putting the little dots onto the tape for us. That way we're able to do the calculations that we need to for this practical. So let's see how we go about doing it. So the first thing, we set up the apparatus as I've just shown you in the diagram. Then you switch your ticker timer on and you let your trolley move freely. You just take your hand off the trolley and let it roll down the slope. Okay, so you're not pushing it or anything like that, you just let it go, right? Switch the ticker timer off, take the tape off. Now, you take the trolley back up to the top. Okay, so we're going to take the trolley back up to the top of the slope, and this time we're going to add a mass piece. So the first one, there is no mass piece. You just let it slide down the slope with your ticker tape attached. The second time, you put a new piece of ticker tape on, take the trolley up to the top of the slope, and now you put a mass piece with some string down at the front or down at the bottom so that it'll pull it down the slope a lot faster. Okay? And you can do that several times if you want. You can change your mass piece a few times so that you don't just have one. Remember, it's a good idea to repeat the same thing more than once if you're able to, so you can improve your accuracy and so that your values are more reliable. But if you don't have that opportunity, you can only do one per mass piece. Do it anyway so that you can see how the things change. Okay, so once you've repeated changing the mass pieces, you're now going to calculate the acceleration of the trolleys by analyzing the ticker tapes produced. All right, and you use ticker timer, you're going to use the period of the ticker timer, you're going to use the distance between the gaps and the number of dots that there are on the tape. There's a whole lot of different ways in which you can calculate it. Once you've done the experiment though, because we had an investigative question and you would have had a hypothesis, what you expect to have happened, we need to come to a conclusion. And this is the conclusion we come to at the end of this experiment. So I'm going to read it to you. It says the acceleration of the object is directly proportional to the resultant force provided the mass of the object remains constant. So what does that mean for us? That means that we've proved Newton's second law, which is actually a really cool thing to do in the lab. We don't need this really fancy machinery and go to super duper laboratories. You can do it in your classroom with trolley, ticker tape, few mass pieces, and we can prove what Newton said a couple hundred years ago. We can prove it in our classrooms. I think that's pretty cool. Okay, now we get on to the fun stuff. I know some of you who don't like doing questions are going, oh no, questions are terrible. We're going to go through this slowly so that you know how to do this properly. And so when you're faced with this in your test, this will become easy for you. It's not something you have to worry about or panic about. Go through the method so that it works for you. Okay, so follow with me. First question. A 10 Newton force is used to pull a toy train, which has an engine and another cart attached. The train engine has a mass of 1 kilogram and the cart has a mass of 500 grams. The track is smooth, therefore there is no friction. Okay, that's really good to know. The track is smooth, so there's no friction. So let's have a look at the information that we've got. Firstly, we've got a force of 10 newtons. We've got the mass of the engine, and we've got the mass of the cart. Now remember, in our calculations, mass must always be in kilograms. So what you're going to have to do here is you're going to have to do a conversion. You're going to have to go from grams to kilograms. Okay? Have a look at our cute little picture. I wish I could go on a train like this. This looks like fun. Now comes the interesting part. How do we solve this? We need to calculate the acceleration of the train. Okay, so what I'm going to do, I don't expect you to get an answer yet. I'm going to give you 2 minutes to just think how you're going to solve this problem. How are we going to do 1.1? How are we going to calculate the acceleration of the train? And then 1.2, how are we going to calculate the tension in the link between the train engine and the cart? Okay, so 2 minutes. Don't have to get a full answer. I just want to know how you're going to attack this problem, how you're going to start answering these 2 questions. All right, so 2 minutes to try and answer that with a friend, with a group of you. 2 minutes to go. Let's start now. Time's up. Let's see how you attack this problem. Let's go. So the first one, calculate the acceleration of the train. Now, hopefully, somebody is saying somewhere. If they're not saying it out loud, then hopefully you're all saying it in your head. The first thing we do is draw a diagram. Doesn't matter if it's got anything to do, if they don't ask you to draw a diagram, doesn't matter. Still draw diagrams, draw all the forces acting on the object. It makes things so much simpler when you've just got that simple picture to look at and you can work out where things need to go. So that's how I'm going to start. So even though it says calculate the acceleration of the train, I'm going to draw my diagrams first. So I'm going to do one for the train and then one for the cart. So let's have a look. So for my train, what do I have acting on it? All I need to worry about is all the forces acting in the direction of motion. I don't need to worry about gravity and I don't need to worry about the normal force. So what I've got here is I've got 10 newtons pulling to the left and I've got tension to the right. So this is for my train. Then for the little cart, all I've got acting left and right, oh, and I can't draw straight today. All I've got acting left and right is my tension acting to the left, and that is my cart. Okay, so I've got my force diagrams now. Now let's have a look what I can do. My equation that I'm going to use is F net equals ma. But remember, your net force is the sum of all the forces acting. So because I've got two objects, it looks like I'm going to have simultaneous equations. I know you're groaning, going, oh no, it's maths again. Yep, physics enjoys maths, maths enjoys physics, so we've got to learn to love both of them. So let's start with the train. For my train, I'm going to say that F net equals ma. Everybody's happy with that. Okay? So my net force is 10. Or should I say my applied force is 10. Minus my tension is going to give me mass times acceleration. Okay? And I can actually substitute in my mass, because the mass of the train they told us was 1. And I'm going to end up with that. I'm going to leave it at that for now. For my cart, again, I'm going to go F net equals ma. And because the only force acting on my cart is tension, I'm going to say force tension equals ma. And if I substitute in the mass, remember, I'm just going to put it up here in a different color. The initial mass was 500 grams. To convert it, we're going to divide by 1,000. So we're going to end up with 0.5 kilograms. So here, I'm going to put in 0.5, and I'm going to multiply it by A. Okay, now that's fine if you look at it, but it's not very tidy. So I'm going to tidy up a little bit, and I'm going to give these numbers. So let me tidy up like this. I'm going to make tension or force tension the subject of our equation here. So that means I'm going to need to move things around a little bit and make this equation 1, and this one can stay as it is. I'm just going to give it the name or a number. I'm going to make it equation 2. What I'm then going to do is I'm going to substitute 1 into 2. You can say add 1 and 2 or substitute 1 and 2. So I'm going to substitute make sure I'm spelling it right, substitute 1 into 2. Okay. I want to make sure you understand why we're substituting 1 into 2. So just stick with me here. We've set our equations so that force tension is the subject of equation 1 and force tension is the subject of equation 2. They are the same force. They're the same tension force. So we're using them as our common factor between the two, and we're therefore going to make our two different diagrams or our two different equations equal to each other because we have a common factor. So that is why we're able to substitute 1 into 2. It's the beauty of simultaneous equations. let's carry on from where we left off, see where this leads us. So I'm substituting 1 into 2. That means I'm going to write 10 minus a is equal to 0.5a. I want to collect like terms, so I'm going to have 10 is equal to 1 plus 0.5, that should be a, plus 0.5a. So 10 is equal to 1.5a, which is fine if you want to leave it as an equation, but we don't. We need to solve for acceleration. So we're going to go 10 divided by 1.5, and if you double check me on your calculators, you will see that I'm going to get a value of 6.67. But remember, in science, unless there is a unit, our value is meaningless. So our acceleration is 6.67 meters per second per second. You've done a lot of work, some good calculations there. We're going to take another quick break, and we'll carry on with this question after that. See you after the break. Welcome back. Let's get back to our train question, see if we can solve the next part. So let's go. Part 2 asks us to calculate the tension in the link between the train engine and the cart. Now remember, from our previous calculation, we had worked out that acceleration is equal to 6.67 meters per second per second. So we have two options now. I'll show you both. We can substitute this acceleration into equation 1, and equation 1 was originally 10 minus force tension equals A, and we're going to go 10 minus force tension equals 6.67. So if I solve for tension, I'm going to end up with 3.33 newtons. Or I can substitute A into force tension equals mass times acceleration. I'm trying to solve for force tension. Next mass was 0.5. We calculated that in our last calculation. And here you're going to see that there's going to be a slightly different answer. I just want to make you aware of it. This is 3.3. This one's 3.4. Both will be acceptable because you rounded off an equation or in the first calculation in 1.1. So we are aware of the calculation rounding off. And so when it comes to marking, we'll be aware that you've carried through that. Right, so we've done a simple, relatively simple horizontal calculation. I want to now take you onto a vertical calculation. Let's have a look what I've got in store for you. A helicopter. So let me read it to you. A helicopter lifts a load vertically off the ground. Okay, so we're going in that plane. It accelerates at 5 meters per second vertically upwards. First question, draw a labeled free body diagram to show the forces acting on the load. And 2, calculate the lifting force exerted by the rope on the load if the mass of the load is 100 kilograms. Okay, so I don't have a really smart helicopter for you, but what I do have for you is a challenge. So again, time for you to do some work. I'm going to give you a minute because it's just drawing a diagram. I'm going to give you a minute to draw the free body diagram for this question. So 1 minute starting now. Time's up. Let's see what you've got. So if you're going to draw a free body diagram, remember you draw a dot to represent the object. Then going up, I'm going to have an arrow. Now please you draw these with straight lines. I'm drawing my freehand, so in my hand's not so great when it comes to drawing straight lines, but you're going to try and draw it as straight as possible, and you're going to label it. So I'm going to label that force of lift. The other one that I've got acting here, and it's not the same value because there is an acceleration, this is going to be force of gravity. Okay, so let me just point out to you. If you are going to use a short terminology, so FL or FG, please have a key or something on the side where you can say FL equals force lift and FG equals force due to gravity, okay? Because just having these is not enough of a labeling. Okay, so we want you to label it properly. So if you are going to use shortened forms, make sure that somewhere you've just got a key on the side for your examiner to have a look that you mean FL equals force lift and FG equals force due to gravity. Okay, good. I'm sure you all got that one perfectly correct. Let's go on to the next part. Sorry, I'm getting ahead of myself here. I'm getting too excited. I want to show you that next one. Next part, here we go. Calculate the lifting force exerted by the rope on the load if the mass of the load is 100 kilograms. Now, one piece of information we need to bring down is that it accelerates at 5 meters per second per second. What have we got here? We've got the lift force acting in one direction and gravity acting in another direction or in the opposite direction is equal to mass times acceleration. These two together are to give us our net force. Okay? So we need to calculate our lifting force. So our force lift, how do we calculate force due to gravity? We're going to go mass times 9.8 is equal to mass, which is going to be 100 times 5. Okay, now remember, you can break them up, but because it's all acting on the same object, you might find it easier to substitute it into the one equation. So my lift force minus 100 times 9.8 should give me 98. And this is going to give me 500. So again, bring all the terms that are like together. I'm going to go 500 plus 98. So my lift force here should be 598 newtons. And there we have our problem solved. Right. Okay, so we've had an example of horizontal plane, so where the train is pulling the little cart along horizontally. We've just done an example now with the helicopter where we've done vertical motion where we lift up and down. The third example that I want to show you is a combination of horizontal and vertical. Okay, this one now involves a lot more simultaneous equations, so the mathematics gets a little bit more complicated, but I want to focus on how we attack or how we approach this problem first. What do? First thing I do, and I know that questions often ask about draw the diagrams. I like drawing diagrams. In terms of physics, it just helps me figure out what's going on, where to put things, what I'm going to be calculating. So when I read through this question, I will read through it, and then the first thing that I like to do is draw a diagram. So I'm going to do the same with you before we even look at the questions. Okay, so let's read it together. 2 blocks of 3 kilograms each are connected by a rope, are placed on a horizontal frictionless table. That is good news already, that it is frictionless. A third block of 4 kilograms is connected to the others by a light rope over a frictionless pulley. Okay, so frictionless in both cases. So what do we have? We've got block X and block Y are on the horizontal plane, so they're on top of a table, and block Z is in our vertical plane. So remember I said to you that I like drawing diagrams. So for this, I'm going to draw just a free body diagram of X, and it's going to show that there's a force going in that direction, and that's all that's acting on X. Let me make life easier. I'm going to indicate that these forces are tension 1 and tension 2. So then we can label these properly. So that is for X. For Y, we've got a force acting to the right, so that's force tension 2. And we've got a force acting to the left, that's force tension 1. Okay, so that's going to be for Y. Now for Z, here comes our vertical plane. We've got tension 2 acting up. And what do we have acting down? Force due to gravity. Okay. So what I want you to focus on in this case, because we've got the two different planes, we've got going across and we've got going up and down, we need to make sure that we're able to put together equations for each individual block. Okay? We don't want you to add all three together and try and solve it that way. All right? You need to have an equation for block X. You need to have an equation for block Y, and you need to have an equation for block Z. Okay? So let me just show you the types of questions that could be asked here. I'm not going to go through them with you. I want to show you them. There will be plenty of time in future lessons where we talk through Newton in revision, but for now I just want you to have a look at the type of question. It's just keep in your mind that we've now got to combine our horizontal and our vertical. Okay, so the types of questions we're going to get are the following. Something like, calculate the acceleration of the 3 kilogram block marked X. Calculate the tension in the rope between X and Y. Or calculate the resultant force on the 3 kilogram block marked Y. Okay, those are our types of questions. We cannot answer any of them unless we have our equations properly set out. So what I'm going to do is I'm just going to show you how to set up an equation for this sort of system. Okay, we're not going to worry about answering the question. I'm just going to write them out for you. So for X, I'm going to have force tension 1 equals MA. For Y, because this object is accelerating and it's going to be accelerating down like that, tension 2 must be greater than tension 1. And for Z, because it is going down, gravity must be greater than tension 2, and that will give us MA. Okay. We've got a lot in this diagram. We've got 2 different planes, we've got 3 different blocks, we've got 3 different equations. Okay. What you need to remember, draw your diagrams when you see a diagram or a picture like this. Write down your simultaneous or your individual equations so that you can use simultaneous equations. And even if something goes wrong with your maths a little bit later, you have the correct equations and your marker is able to follow through what your thought processes were. Guys and girls, you've done really well today. You've gone through lots of Newton theory. We've done 2 different types of examples, and I've showed you what you can expect if we put the 2 different types together. I know that you'll be able to answer these questions because you're going to follow the rules of drawing the diagram, writing out the correct equations, and then just substituting as you need. Keep trying hard, keep practicing the examples that you've got in your textbook so that your teachers give you, and we will see you again soon.